So in this video and basically in this entire chapter, we're going to be understanding why we need a harness in the first place, why we need a harness for our agent. And we'll begin there by understanding what I would like to describe as the raw model problem. The raw model problem. Now basically, the LLMs that we're used to today, that's our model, are basically text transformers. They are text transformers. Because what they do is that they take a sequence of tokens. This is basically what LLMs read your prompts to be, a sequence of tokens. And based on this sequence, they try to predict the next set of tokens. So basically, their output is a probability distribution over the next token. And they keep doing this on and on and on and on until a full response is generated. And that's it. That is what these models do. They are basically text transformers. They're basically text transformers. They don't create any side effects. They don't have any memory. They don't have access to anything outside of the prompt. They basically just transform text. A sequence of tokens go in as your input, and the probability distribution creates the next set of tokens, and they keep generating that until a full response is generated, which they then send to the user. So the intelligence is real. The intelligence is real, but the surface area is limited to tokens in and tokens out. That's basically what these LLMs have been doing. Now, why does this matter? Why does it matter that we understand what this is? It's because most developers, and I assume that a lot of people watching this course are developers or at least are working in the software industry, we often assume that these models are some sort of function in a library. Typical functions that we call in a library or in an SDK, we assume that there are some sort of functions, and what we do is that we call them, they do something, and return a result. That's how most developers will see an LLM, at least when they are interacting with an LLM for the first time. Probably you're calling the generate content function on an OpenAI SDK, and you feel that, oh yeah, I just send in an input, my arguments, and I just get a response because the model does something. That mental model is wrong for models. Models don't actually do anything. They don't take any form of action. What they basically do is describe the doing of things. Yeah, they describe doing things. They don't do the thing. They just describe how the thing can be done or how the thing is done. That's basically what models do. Their surface area is limited to text. They're basically taking your input and describing what the output should look like. So a model doesn't actually take action. They only describe an action. And if you're already familiar with a concept like tool calling, you realize that what the model actually returns is a tool call. The model doesn't call your function. It doesn't call the function that you describe to it. It just describes back how the function is to be called. That is what the whole tool calling integration is based on. The fact that the model understands the function and it can describe how the function can be called, and it can even tell you use it with this argument and that argument. That is the whole thing about tool calling. So it's still within the description of things, and that is the only thing that models can do. That is the only thing that LLMs can do. They can only describe how things can be done. And this leads to several gaps when we actually want these models to operate as agents. Because agents are meant to do things. Agents need to have a real impact in our environment, in the real world. They need to help us get things done. A model that can simply just describe things is not going to cut it. So let us look at the gaps, because it is from looking at these gaps that we can then describe what a harness is. A harness, typically, in plain English, is basically a support system. A harness is a support system. It's what, for example, I used to intern in the telecommunication industry, and one of the things that we did was that we climbed masts. We do climb this telecommunication mast, but we don't just climb it just like that. We wear this safety equipment, and that equipment is called a harness. It supports us, it guides us, it helps us to stay safe. So basically, a harness is a support system for a thing, and we're going to be looking at the gaps that are between a model that can only describe things and an agent that needs to do things. In between those gaps is where the harness then comes in as the support system that helps the model do things. Not just describe, but do things. So let us look at the gaps. because the gaps are what is really going to determine what you need in your harness. So the first gap of a model that can only describe things but not do things is the fact that there is no execution. It can't execute an action. That is the obvious gap. That's the first obvious gap. It can't execute an action. The model cannot read a file. It cannot run a script. It cannot query a database or even make an HTTP connection or an HTTP request when you need to communicate with an external service. The model can't do anything in our environment. It can't do anything in the real world. But we need it to do that. And something has to help the model do that. That something is the harness. So that's the first gap. The second model gap is that there's no durable state. There's no durable state. Every API call on our model is stateless. Anytime you call OpenAI through its API or you call Anthropic's Claude models through their APIs, everything is stateless. Everything is stateless. There is no state that is being maintained on the OpenAI or Anthropic servers. Everything that the model needs to know has to be referred to the model each time it needs to return a response. What you understand as conversation memory is basically an illusion that is created by simply sending all the previous messages back into every subsequent call. It's an illusion. You are just basically taking everything that you have received as response and everything that you've sent as a message in the chronological order as a conversation history. You are replaying it every single time into your model call. That is what the conversation history is about, and that is why your models that you've been chatting with, most especially through your chatbots, Gemini, Claude, and ChatGPT, that's why it feels like they remember stuff. They actually don't remember anything. The entire message history is just being replayed. And once the context fills up or the session ends, the model remembers nothing. The model remembers nothing. When your session in a particular context window is filled up, the model cannot remember anything beyond that. Yeah, it has maxed out its working memory. But for an agent that is going to act on our behalf, we need it to remember things. We need it to remember us. We need it to remember the activities we've done. We need it to remember that alarm we need to set. We need it to remember what we discussed 3 weeks ago. That persistence is not something we can get from the model. Like I said, the model remains a text transformer. We can't get that persistence from a model. We need to get it from the harness. So this is the second gap that we need our harness, our support system to fill up. The next gap that we'll experience by using just a plain LLM is that there's no fresh knowledge. There's no fresh knowledge beyond the model's cutoff date. That's the model's training cutoff date. It doesn't have any knowledge beyond that. So if the model, let's say, okay, this week, or was it last week? This week, Arsenal won the Premier League. Yeah, Arsenal won the Premier League. This is the, today is the 22nd of May. So Arsenal won the Premier League this month. And this week, to be specific. Let's say our model's training cutoff date was actually March of 2026. And we ask it, who won the Premier League in 2006? It won't remember. It can't remember that because its training cutoff date was March 2026. And by that time, the winner of the Premier League had not been decided yet. Or we ask it who won the NBA title. We don't, even till today, we're still in the NBA playoffs, the conference playoffs. So, yeah, the conference finals. So, we don't know who won that yet. But if a team eventually wins it down the road, I think around July or something, this model is not going to know. This model is not going to know because its training cutoff date is March 2026. Anything it needs to know has to be injected through the prompt. It has to be injected through the prompt. You have to keep feeding it into the prompt. That is actually called in-context learning. You have to feed it into the prompt. There's no way for it to get fresh knowledge aside that. There's no native way for it to just pull fresh knowledge aside it being fed into the prompt. So our harness also has to take up the job of passing in any fresh knowledge that our agent needs, either by querying a website, querying our database, any sort of query it needs to do, any sort of knowledge base it needs to be exposed to so that we can keep feeding it into our model. Our harness has to do that job. The model itself is not going to do that job. Another gap is that there's no way for the model to actually verify what it does. Of course it can output a response, but it can't fact check itself. Yeah, I know some of you might say, yeah, why don't you feed it into another LLM and it will verify whether that LLM is right. And yeah, that can work to an extent. But when it comes to truth, not things like probably just verifying whether a document is well written, whether it's grammatically correct or stuff, when you're trying to verify truth, when you're trying to ground truth, stacking layers of unpredictability, that's just having models verify each other, it's not going to cut it. So there's no way for a model to actually verify that what it is doing is correct. It can generate code, but it cannot run the code to see if it works. Yeah, it can run it. It can produce a summary, but it cannot say, yeah, let me compare that summary with this truth to check fidelity. It can only claim correctness, and it does that with a very high level of confidence, which is one of the limitations of models today. But claiming and verifying are different operations, and only one of them is available to the model, which is claiming. The model can claim. In fact, the model will do a lot to claim. If you tell it is wrong, it will also accept, but probably you are wrong too, so it doesn't even know whether it's actually correct. Yeah, models are getting smarter these days. I think from Opus 4.7, I'm beginning to get a little pushback sometimes when I tell it, yeah, why is this? I thought this was this. Why are you doing this like this? Sometimes it tries to kind of argue why it does that. So you're getting smarter, but still, these are probabilistic machines with no soul, so they can't actually, I can't take their word 100%. So the model can't verify that it is correct. The harness has to be responsible for creating a verification system around the model's output. Yeah, it has to be able to create a verification system around your model's output so that you can know that, yeah, this is actually correct. This is actually good. For example, these days, when I use Claude Code. When it generates code, it tries to run it within a sandbox so that I can verify that, yeah, this code works. Then it returns its response and say, oh yeah, this is correct, this is valid, and all that. And that's because a harness has been built around it. But the model, the pure model itself, cannot do that. Yeah, it can't do that. Now, the final gap when we're trying to translate a model into a fully autonomous agent is that the model has no environment. The model is without an environment. It doesn't have a body. Yeah, it's basically a brain. It doesn't have a body. It's not something that's sitting inside a Linux box with Python and Git installed. No, it's not sitting anywhere. It is basically just a mathematical function being evaluated on a GPU. If you want to use something like pandas, say you want to install pandas, or you want to use a browser, something actually has to install pandas. Something actually has to give you a browser. And those type of environments is something that we need the harness to provide. It is the harness that is going to be providing the environment, not the model. So this is also another harness responsibility. Execution is a harness responsibility that's taking actions. State is a harness responsibility. Getting fresh knowledge into the context of the model is a harness responsibility. Verifying that what the model outputs is correct is a harness responsibility, and providing an environment in which the actions described by the model can be executed is also a harness responsibility. So I believe from these gaps you've been able to understand why we need a harness. But in the next video we're going to run a piece of code that is actually going to show these gaps, and then we can start filling these gaps by introducing features that close these gaps into an agentic harness. So in this video, we're going to be running a simple demo that is going to help us to visualize and confirm a bunch of the gaps that we discussed in the previous video. In the previous video, we saw gaps like no execution, no durable state, no environment, and the rest. And we're going to be running a simple script. This is a simple OpenAI script that is using the OpenAI SDK. We are creating a client, and that client is calling the OpenAI API. And what we're doing here is that we're calling the GPT-4o mini model, and we're calling it as a user, and we're telling it that we want to read the file article.txt in this directory. We're just saying in this directory. So we're assuming that it should just assume the directory that the script is in. It says summarize it in 3 bullets and save the summary to summary.md. So we are telling it here to perform an action. We're telling it to read a file, summarize it, and write a file. And if you look at these three actions, that's reading a file, summarizing it, and writing a file. These three actions, based on the gaps that we discussed from the previous video, only one of them can be performed by the model. Yeah. Reading a file, no, the model cannot do that. Summarizing the file, yes, the model can do that. Writing a file, nah, that is another file system responsibility. But don't take my word for it. Let us just look at this simple plain call to the OpenAI API. This is what the simple call looks like to a model. Nothing added, no harness filling any gap, just a simple call. Let us run this code. I've already added my OpenAI API key, which is something that you need to run this code. You need to add it with export OpenAI API key. Then you pass your key here. So if you're running this code, make sure you do that. And I also have the article here, article.txt. It's just a random article about the printing press, but the content doesn't matter in the scope of this lesson. So we're going to run this code by saying python demo.py, and we're going to see what the model does and how it surfaces a bunch of the gaps that we have discussed. Okay, so the response is back. Let us read this and see what the model tells us. It says, I can't directly read files or interact with your file system. You see, it immediately recognizes its limitation. It says, I can't read files or interact with your file system. So it knows it can't access files. It then goes further to say, but I can help you summarize the content if you provide the text from the article. You see here, summarization, it is telling you what it can do. This is what I can do. It first tells us what it cannot do, which is the file system operations. Then tells us I can summarize because it's a text transformer. It can do text. Then says, please copy and paste the contents of article.txt and I'll assist you in creating a summary. It's describing what the action should look like. Give me the file and I'm going to create the summary. You can then save the file yourself. Yeah, you can go save the file yourself. So you see the model exposing its gaps and also indicating its capabilities. And the gaps that we've discussed are surfacing in just this response. First, nothing happened. Nothing happened. If you look at the file system, nothing happened. No summary was created. There's no summary.md, which is a lesson because this is not telling you that the model failed. This is what the model exactly does. It just tells you what it couldn't do gracefully. But in the outside world, nothing changed. Nothing changed. So the model cannot act. We've seen that. And that's the surface area problem in its purest form. The model's only channel of output is text. It can describe text. It can recommend action. It can decline action. It can even claim action. Sometimes the model will just outright lie to you that it created the file. But when you look at your environment, you don't see anything. So it can even claim that it did something, but there's no action. And we all know that the gap between describing something like writing a file and actually writing the file there are two different things. There's a big gap between that, and that is something that has to be closed. That's a gap that has to be closed by the harness. So in this demo, we've been able to see the no execution gap surface, which is the fact that the model couldn't read or write the file. And the model was very, very transparent about that. It correctly said so. There's no environment, so there's no file system available to it in the first place. There's no file system. It doesn't even know where to find the article.txt because there's no environment that it can access. Also, there's no durable state. That might not be like outrightly visible right now that there's no durable state. But even if we gave it the article and it was able to generate a summary, and the following turn we ask it about the summary, it is not going to remember that summary. It's not going to remember both the article and it's not going to remember the summary. So there's no durable state. For example, if I go here and I change this and I say, let's just say, but can you at least tell me the name of the file I asked you to summarize? Because earlier we told you that there's an article.txt. So even if it doesn't know what is inside, Even if it doesn't know what is inside the article.txt, we have told it that there is an article.txt. Now, we are asking it for the name of the file we asked it to summarize. Let's see what it tells us. See, I don't have the ability to access files or remember previous interactions. It is literally telling us the gaps. And these are the gaps that your harness needs to fill. If you want to convert your model into an agent, filling these gaps is what the harness is all about. So it tells us, I can't remember previous conversations or previous interactions. If you provide the title or content of the file, I'll be glad to summarize or discuss it. Now, I didn't get the summarize from the previous prompt. We literally said summarize here. So you kind of remember that we're talking about summarizing a particular article. So the long form of it is that your harness is every piece of code, configuration, and execution logic that surrounds the model and makes it capable of acting, remembering, learning, verifying its output, and persisting state. That's basically what the harness is all about. That's what we're trying to drive at with the previous lesson and this lesson. Everything you are wrapping around your model to make sure that it is capable of taking actions, it can remember past interactions, it can learn from previous conversations, it can verify its output, and it can also persist files and information to state or permanently. That is what a harness is all about. Everything in an agent's development that is not the model, everything that is wrapped around the model to make it function as an agent, everything that closes the gap between description and action is the harness. And in coming videos, we're going to be looking at each of those harness items one after the other. So in this video, we're going to be defining the harness. By the way, I just noticed this definition has an error here, so let's fix that. Okay, that's good. So like I said, we're going to be defining the harness. Now, the harness is not just one thing. It's actually a stack of several concerns. 6 of them are core. So those are the 6 we're going to be looking at in this video. And they translate into every harness you see out there. Cloud Code, Codex, any type of harness you see out there, OpenClaw, they all contain these 6 components. So, like I said, the harness is not just one thing. It's a stack of 6 concerns, and each of which can be designed well or badly. And each of these concerns corresponds to a specific class of gap that we have looked at. And if you see your agents failing in production or being broken, yeah, this component designs are going to be one of the reasons why you are having that failure. Subsequent videos after this is going to go into each component in detail, but here we're just going to be looking at each of them at the surface level. So in the previous lesson, we looked at the gaps. We even saw a code demo to show us those gaps. In this lesson, we're going to be naming the parts that fill those gaps. The 6 components, like I said, the 6 core components. And once you have these 6 components properly understood, you will be able to participate in any conversation about agents. Trust me, you're going to be able to participate seamlessly in any conversation about agents. Whether it's about designing them, debugging them, comparing different tools, reading agent papers, you would be able to easily flow with the vocabulary. Yeah, you will now stand literate about agents once you can have these 6 components nailed down. But before we go into the components, let us first look at this formal definition of what an agent harness is. So let's look at it. It says, the harness is the engineered system surrounding a language model that turns its single output channel, which is text, into action, persistence, and measurable behavior. Let's take that again. The harness is the engineered system surrounding a language model that turns its single output channel, which is text, into action, persistence, and measurable behavior. Like I said, the harness is basically the system that is translating the textual output of your models into agentic operations. That's what the harness is doing. And We have agentic actions, we need to persist state, and also we need to be able to measure the agent's behavior. We need to be able to understand what it's doing. But let us take that one by one. Let's start with action. So action is the first main verb in this definition. And what the harness basically does to ensure that models can take actions is that it gives the model a surface area that is beyond text. Yeah, it gives the model a playground. It gives the model a workspace. So it gives it a file system, it gives it a code sandbox, and even things like web access. It just gives it different environments for it to play in. File system, code, execution environment, access to the internet, databases, many more. So it gives it a surface area that is beyond text. And what we've described is basically an environment. Yeah, it gives it an environment to operate in. But not just an environment. It also helps it to execute the things that the model describes. Yeah, it executes the things that the models describe. Can you guess what that is? Can you guess how it does that? Yup, tools. Tools. Yeah, it gives it tools to operate and do what the model describes. The model describes an action. The harness provides an environment that it can execute the action, and it will be able to execute the action through a tool. Yeah, tools execute inside an environment by executing an action described by the model. That is the action part of this definition. Next, let us look at persistence. So we already understand that our model cannot retain state. And this is where persistence comes in. Persistence comes in, and this persistence can be within a session or across sessions. Two flavors of persistence for the agent to be able to operate. So it has persistence within a conversational session, what we're going to later on understand as short-term memory. So that is the memory within your conversation, your current conversational session with the model, and also what is known as long-term memory. And long-term memory can be shared between different sessions. It is more like what the agent is learning about the user and some ground knowledge that the agent is always working with. So we get to achieve persistence for short-term needs and for long-term needs. And finally, we have measurable behavior. We need the harness to be able to expose what the agent is doing so that as engineers, we can evaluate, we can debug, and we can also get enough information to improve the agent, to improve the harness. To improve the agent's harness, we must be able to extract logs and traces and any form of visibility into the agent's actions that can help us improve our harness. So, from this definition, we've seen action, which is done by tools in an environment, persistence, which is implemented in the short term and the long term, and measurable behavior. These are three core behaviors that will build into a harness to get agentic behavior. Now we're still talking about attributes. Let us now look at the 6 components that make this happen. Welcome to the components board. These are the 6 core components that you're going to find in almost every standard harness. Every standard harness should have these 6 components. I've not seen a harness out there that doesn't have any of the 6. And the first one is the loop. The first one is the loop. Now, why are we calling it the loop? In our demo, you'll realize that we can only call the model once, and each call is stateless. So, if we are to have a conversation with the model, and we need to call it in multiple turns, that means we have to wrap a loop around it. And this loop is to take the conversation history and feed it into the model for every interaction we have with it. To take the conversation history each time and feed it back into the model. That's why we call this the loop. But basically, it is the control structure that calls the model in multiple turns. It's also in charge of dispatching tools and decides when the conversation stops. It's basically the orchestrator around the model. But like I said, we have a video dedicated to each of these components, so no need to go deep into them now. Just understand that the loop is what guides our conversation with the model and makes it multi-turn. Component number 2 is the tools. The tools. Yeah, the items that actually perform the operations. These are basically functions the model can invoke in order to have an effect on the outside world. It can be to read a file, to write a file, to delete a file, to create a directory, to query a database, to fetch a web page, and many more. The tools. This is where you start getting real agentic behavior by wrapping a harness around your model. Next, we have the context. The context. Yeah. This is everything you feed into the model for every call. Remember I said we call our model in a loop in order to have a multi-turn conversation with it. Now, every time we call it, we have to feed it a prompt. And that prompt has to contain everything the model needs to be able to give the appropriate answer. Everything the model needs to give us the appropriate answer. That everything is the context. The context. That is what is fed into our model on each call. And it contains things like the system prompt, the conversation history, retrieved knowledge from static sources, and even tool results. The results of calling tools can also be fed into the context. So that's the third component in a standard harness. Then we have as number 4, the environment. Yeah, the environment. This is the runtime the tools operate inside. Yeah, if you say read a file, the tool needs to be able to point to a specific location to pick the file. If you say write a file, the tool needs to be able to point to a specific location to write the file. So the runtime the tools operate inside is the environment. And this can be a file system, this can be a shell, it can be the network, or even be a sandbox code environment with boundaries. So the environment is the 4th component in our standard harness. The 5th component is the memory. Yeah, the memory. We need to persist state. So as we loop around, as we continue to loop around, each iterations, we need to persist state for a session. In the short term, we persist state for that session. In the long term, we extract certain useful information from each interaction and plug it into a more persistent storage so that we can feed it in whenever necessary in any conversational turn. So we have the memory that I've described earlier as being divided into short term and long term. And finally, as our 6th component, we have the observability. The observability. The harness also needs to contain instrumentation that exposes what the agent is doing. Yeah, we need to be able to see everything from logs, from traces. We need to be able to expose the details of every single action that our agent is taking. We also need evals. We need evals to be able to benchmark our agent against known tasks and see its output to see if we're getting quality results. We also need information to be able to debug our agent. So here are your 6 components for a standard harness. The loop, which is the control structure that guides your conversation with the model. The tools, which are your action takers. The context, which is a construction of information to be fed into the model to evoke the right response. The environment, which is where tools are going to operate. The memory, which is how you persist state. And observability, which is how you expose the agent's operations in order to debug and improve it for better impact. In this video, we're going to be looking at the very first harness component, and that is the loop. The loop, yeah. This is the orchestrator. It is the control flow that wraps the model. Remember we said the model needs to be called multi-turn. Most usage of the model needs to be called multi-turn. Now, it's not that you can't just call the model once and get a response. You can always just make a single call to the model and get a response. But when it comes to agentic interactions, most of the calls to the model will be multi-turn, meaning cycles of this operation. And this is where you need the loop, which is the component we're discussing, to wrap around the model, to be the director, to be the conductor of the interaction with the model. It will take user input, pass it to the model, get the response, and feed back the conversation history into the model. So at the end of the day, you get to have something like this. This is the agent loop in its basic form. You call the model with a prompt, you get a response. That response gets packaged into a conversation history and sent back to the model. The conversation history is basically a combination of what has been said so far plus the new prompt. This is the most basic form of your loop. You prompt your model, get a response. That response goes into the conversation history. The conversation history is combined with another prompt and you feed it back into the model. Get a response, gets packaged into the conversation history. That conversation history is tagged onto the new prompt and it keeps going on and on and on like that. Now, this cannot run forever, so definitely you will need a termination point. You will need to know when this is to stop. The loop is also what does that. So at every response point, we always do a termination check. And this check basically asks, are we good enough? Do we have everything we need for a response for the task? If not, we go again and we prompt. We go again and we prompt. But if we do, we then just send our response to the user. We send the final response to the user. So this is the basic form of your agent loop. Now, there can also be a tool call, which is very, very common in conversations with the model that require agentic operations. So, most likely we have a tool call. How does a tool call come into this? If we get a response, and that response has a tool call, then we'll need to execute the tool. We need to execute the tool, we get the results of the tool, and those results are fed into the conversation history and used to reprompt the model. If we don't get a tool call, we'll simply go on with our regular business, which is just tacking on the new response to the conversation history and tacking that to our new prompt. So if there's a tool, we execute the tool in our environment, get the tool results, and send it into the conversation history as a tool call result. If we don't get a tool call, business goes on as usual. Now, this is how the loop operates in its most basic form. This can really get very, very fancy. This is where your React pattern comes in. This is where your plan execute pattern comes in. This is where your multi-agent orchestration, sub-agents, and all those kind of stuff come in. It can get that complicated. But in its simple form, you're basically looping calls around your model. You are constructing a conversation history, which is a chronological order of all the user messages, response messages, and if there's a tool messages. And you need a termination condition to be able to know when your result is sufficient so that you can pass a response to the user. This loop cannot go on forever. And also, when you encounter a tool, you execute the tool and you pass the results of the tool into your conversation history. If you don't encounter a tool call, you just simply go on with business as usual, maintaining your conversation history and making sure that every new prompt includes the conversation history. So this is basically how the responsibility of the loop looks like in your harness. Now, what does a good loop design require? And we have kind of discussed some of them as we were looking at the loop. But first, you need a termination condition. You need a termination condition. The model needs to say something for you to know that, yeah, this is where we stop iterating. And this can be as simple as the agent just saying done. You can tell the model to say done, let's say in capital letters. So you can scream done, and immediately your loop sees that particular sequence of characters is just going to terminate. It's going to terminate and return the final answer to the user. There's also a stop configuration that you can configure. There's something called stop sequence or finish sequence. When you're using the OpenAI SDK, there's a setting called stop sequence, I think, or finish reason, or so, I think finish reason. Some of them probably call it stop sequence that you can configure to make the model stop. Once it encounters that, it just stops. You can give it a character. You can say when it sees a pipe, when it sees a dot, and you can make sure that in your prompt, you're specifying that okay, yeah, when you read these certain conditions, when you feel it is good, just output the word done or output the character pipe. Also, you can have something like a step budget. You can have a step budget. You can say after every 5 iterations, just give me the final answer. Yeah, once this loop count is up to 5, just give me the final answer. So to do that, you know that you have to maintain the loop count so that as you loop for every conversation, you are incrementing the count. 1, 2, 3, 4, and once it's 5, you just say, yeah, once anything you get At the point of 5, just return it. Just return it to me. So you can have a step budget. Some of these models also have a configuration for this. Some call it max iterations, and some frameworks also like LangChain have configurations for this. So you can have a step budget. Also, you can also terminate when a error threshold is hit. Probably you keep getting errors, probably from 2 results, you keep getting errors, and you can tell it, yeah, if you get 3 errors, just terminate the process and return what the final answer is. Just report the error. So that's one attribute of a good design. Another attribute of a good design is to have sensible error handling. And what that means is that don't crash the loop when tools fail. Yeah, don't crash the loop because a tool fails. If a tool fails, undo the error and pass the error message into the conversation history. Undo the error appropriately during the execution and pass the error message into the conversation history so that the model is the one that gets to report the error. The model reports the error. So basically, the model is reporting the error as an observation. So that's another thing. Third, every good loop must have a shape. It must have a shape. It must have an architecture. It must have a pattern. What you've described here can be argued to be the React pattern. That's the reason and action pattern, the React pattern. So every loop must have a shape. There's also the plan then act pattern. So you can implement that. You can implement a multi-agent pattern. You can go that complex if your agent requires it. You can also do deep recursion. For example, you must have heard of something called the Ralph loop. Yeah, the Ralph loop. You can do deep recursion or do like a orchestrator worker pattern. Basically, your loop needs to have a shape. The loop around your model needs to have a specific shape, and there are standard architectures that you can use like the React pattern, the plan then act pattern, a multi-agent pattern, or a deep recursion pattern like the Ralph loop. The shape of your agent is what determines the kind of tasks that your agent can do. Just as we know that some agents cannot perform deep work because they don't have something like the Ralph loop implemented. Some agents cannot also be multi-agent because their loop does not have that type of architecture. So the shape of your loop is what determines the capability of your agent, what tasks your agent can perform. Now, to wrap things up in this lesson, let's do a simple case study and look at a harness in the real world, Claude Code, and how we can detect the loop behavior that Claude Code exhibits, how it fixes bugs, how Claude Code fixes bugs. Now, when you ask Claude Code to fix a bug, it doesn't just make one model call. It doesn't just make one call to the model and the model will just magically fix the entire bug and return a response. No, it makes many calls. It makes calls to read the file, edit the file. It would also run tests, read the error messages, and go back to editing the file again with what it has learned about the errors. The loop is what makes this multi-step process possible. This multi-step behavior that Claude Code exhibits when it is fixing a bug, the loop is what makes it possible. The loop is also what makes it decide when to stop. After running the tests, when it reads the errors and it sees that all is clear, it is confident that the task is done. And that is when it now returns a response to you that it is done. This is not a one-shot operation. This is evidence that a loop is in operation, running these processes, iterating over them until it is clear of errors. It can then report back with confidence that the task is done. So that is the harness loop. A whole chapter has been dedicated to this component for us to actually build our own loop around an LLM. So consider this your intro. In that chapter, we're going to be going into more details and we're actually going to be building our loop from scratch. In this video, we're going to be talking about the second component. By the way, this is component 2, not component 1. Yeah, forgive me for copy and paste. Yeah, this is component 2. The tools. The second component that make up the harness, and that is the tools. Now, what are tools? Tools are a set of functions that the harness exposes to the model. The harness gives your model access to these tools. The model can then request a tool by emitting a structured tool call. It emits a structured tool call that suggests a tool with the arguments that the tool should be called with. The harness then executes the tool and returns the result. And that result is passed back to the model as we've seen the loop do? The loop is going to take care of passing the result back into the model. So that's basically what tools are. Tools are the model's surface area into the world. Every gap from the first lesson, that is execution, fresh knowledge, environment, and all that, a tool helps to close it. A tool that the harness provides helps to close any of those gaps that we discussed when we were talking about the gap between translating our models into agentic assistants. And yeah, that's basically all you need to know about the tool. They are just functions that the model can describe how they are to be called. The harness then calls them and they execute within an environment, and their results are passed back to the model to continue its conversation as orchestrated by the loop. Now, what does a good tool design look like? First, you need a set of small and well-named tools that compose very, very well. Yeah, small tools focused on a particular action, well-named, so that the model can recognize them and recognize their function, and tools that compose together. For example, you have a bash tool and a read file tool. These are two small tools, well-named, and they compose together. This is better than having like 15 specialized tools. There's a lot that can be done with a simple bash tool and something like a read file tool or a write file tool. Also, you need your tools to produce clear structured outputs. You need them to produce clear structured outputs. Even if they're going to be outputting errors, it needs to be clear and well structured. This allows their output to be easily read. The model has to be able to differentiate between success and failure from what the tool is giving it. The model has to be able to know whether the tool failed or it succeeded and be able to read the result clearly, whether it's a success result or a failure result. Also, your tools need to be sized so that the model can use them very, very well. They need to be sized for efficient use. So let me break this down. Your tool should be sized in a way whereby if you want to perform a simple operation like read file, it doesn't have to call 5 different tools. Each tool should do enough that the model is not drowning in tiny operations. You want to read a file, just read a file. Don't have a tool that is called get file name. You have to call get file name first, then you have to call get file extension, then you have to call name file, which tags on get file name and get file extension and joins them together. Then you now have read file contents, all just to read a file. No, don't oversplit your tools. When an operation is simple, create a simple tool around it. Don't break it down and make it more granular. Don't go crazy on how much you're splitting down your tools. And as you're doing that, also don't make your tool do so much that we cannot pinpoint the actual step where something went wrong. For example, you create a tool called Analyze Web Page, and that Analyze Web Page is doing so much. It's fetching the web page, it is parsing the content, it is detecting forms, it is filling forms, it is getting form outputs, it's calling APIs, it's querying databases, it's querying knowledge sources, and it's just doing so much that when such a tool fails, the model can't clearly say that this is the step that failed, this is the part that failed. It will just say the tool failed. To just say the entire tool failed, and we cannot detect which exact point that tool failed. So, focused tools that are well sized for their specific operations. Don't create robust tools that do too much. Composability over monoliths. Composability over monoliths when it comes to defining your tools. Make them sized for efficient use. Not too granular that we now start calling 10 different tools to perform one operation, and not too bloated that when they fail, we can't actually pinpoint the step where something failed. So, those are some nuggets you should keep in mind for constructing your tools. Now, to wrap things up, let us do our case study looking at an agent in the wild. And that will be Cloud Code. We're still going to be going with Cloud Code. Now, Cloud Code has a tool surface that is small and deliberate. In Cloud Code, you get to see small focused tools like read, edit, bash, glob, grep, and many more. Now compare this to an agent with like 50 bespoke tools. Almost every time you have another peculiar operation you want to perform, you have to create another bespoke tool for that particular operation. But Cloud Code gets to do a lot with these simple tools. Read, edit, bash, glob, grep. It gets to do a lot with this set of simple tools. Because the Cloud Code harness design bet is that a competent model with sharp general purpose tools beat any constrained model with specialized tools anytime. Anytime. Small, sharp, general purpose tools beats specialized tools anytime. So make sure that you create focused tools, just as we've mentioned in our best practices, focused tools, and do your best to stay away from creating very, very customized tools. Like I said, always favor composability. The way Claude Code has decided to create its tools this way is an actual decision that they decided to go with, and it shapes the entire feel of the product. Even a tool like OpenClaw, or rather a harness like OpenClaw. I remember one of Peter Steinberg's interviews where he was talking about asking OpenClaw to do something that he didn't actually build a tool for it in OpenClaw. He just has a bunch of these general purpose tools, and he just has his OpenClaw agent to I don't know, was it do a particular research or do something on his computer. I think he wanted to just prompt his agent from his Telegram to do something on his system, but he had not built any specialized tool for that, and the agent was still able to get it done. And by the time he looked at the logs, he realized that the agent was able to use a lot of his base tools, compose them together, create a plan, and be able to get that task done. That is the power of having focused, general purpose, composable tools over highly bespoke ones. So yeah, going forward, as we build our file system, we have a chapter dedicated to file system. We build our file system. We have a chapter dedicated to having a tool registry. So we're going to be building our tool registry. And we're also going to be adding our bash and code execution tools. And as this course progresses, you're going to be seeing how we are building all these focused tools and how they are giving us the best performance from our harness. In this video, we're going to be discussing the context. And I want you to listen very carefully here, because this is a very interesting topic. And if you've ever been confused about the concept of context engineering, this is where you actually understand what is going on there. This video is not going to give you all the details about the engineering part, but definitely you understand what it's all about and what is involved. When we get to the chapter that focuses on the context, we will then get to do some context engineering. And this particular topic was quite interesting for me because it makes me understand how powerful the context is and how it translates to a lot of powerful agent harnesses and AI products that we're seeing today. So, as you already understand, the model, our LLM, takes a prompt. It takes a prompt. On every API call, the model is being fed a prompt. But what goes into this prompt? What is contained in this prompt? Because everything that is in this prompt is what is going to determine the type of response that we're going to get from the AI model. It is what is going to determine this response. So let's say we first want to make sure that we are passing instructions to the model that defines who it is, what it should do, that's who the agent is, what the agent is all about. Let's say Claude Code. Claude Code is basically a software development tool. What it's supposed to do, what is its role. We might want to add some backstory and everything. We want to put those type of stuff inside what is known as a system prompt. Yeah, because we want this to always have effect on every single call we make to the model. So we want to have a system prompt in there. We want to have a system instruction. We'll put a system instruction there where we tell the agent, you are a code editor, or you are a code generating agent. You are a software development agent. You can write Python at the level of, I don't know the best Python programmers on earth, but let's say you can write at those guys' level. And we'll give it instructions like style guides and stuff like that, and we'll put everything like that in the system prompt. Well, maybe we might not put style guides, probably, but just key instructions on how to write code. I want this agent to write code, who it is and everything. Let's say we'll put it in the system prompt. So we want to put that because we want it to always have that in its context window and take that into account every time it is generating a response. Let's also say we have something like our style guides, we have our architecture documents, we have some programming language documentation that we feel that it is going to need for it to perform its operations. Probably it wants to write a particular piece of code and it needs to use the observer design pattern. So we want to make sure it has the knowledge for, let's say, Python's observer design patterns and everything. So what do? We retrieve those docs. We retrieve those documents from, let's say, the Python documentation, or probably we have some PDFs. We retrieve them and we put it inside this prompt. So we put in retrieve documents through a process called RAG, retrieval augmented generation. So we augment the generation of our response by retrieving some important documents that this is going to need, that this prompt is going to need, that needs to go into this prompt. So we get that too. So we have that in place. Let's say the current response actually called a tool. Let's say it called a tool. We also need those tool results here. So what do? We simply include tool results. We simply include our tool results. Making sense, right? Then let's say we want some files. We want to attach some files. Probably we have some particular company documents that guide how we write code. I've talked about style guide before, but let's say we have some policies, we have some things that have to do with compliance and stuff like that, and want to make sure that we include them because of the type of code we want to write. Probably we're writing for a fintech application or a healthcare application, sensitive applications like that that would have a lot of compliance requirements and stuff like that. So we just attach some documents to this prompt. And with that, we automatically have another section for attached documents. Attached documents. And we can keep taking more and more and more things that we need into this prompt payload. What we are basically doing, which is collating information through different strategies, through different processes to put inside our prompt to make sure that our prompt has everything it needs to feed into the model so that we can get the right response, is called context engineering. It's called context engineering. Yeah, what we're doing is context engineering. Of course, definitely trying to manage the context window is part of context engineering too. But a lot of the work is in actually grabbing everything that is needed for the current request. Every single thing that is needed for the current request, we're grabbing it in. Because our model calls are stateless. We've learned that from the very beginning. Our model calls are stateless. So it doesn't remember anything. Everything starts from nothing. Every model call starts from nothing. So we have to ensure that we are packaging everything that is required for the current step to be able to execute. So what context engineering simply does is that it converts the question of what should the model know right now, because we know this from the statelessness of the model. It converts the question, what should the model know right now, to what do we put in the context? Yeah, what do we put in the context? Because that's what you're trying to say. Anytime you ask, what should the model know right now for this particular step we want to take? Maybe we want to generate a particular API endpoint, whether we want to generate a model that performs data analysis, we need to ask that question every time. What should the model know right now? Because the model is stateless. What should the model know right now? And what context engineering translates that question to is what should go into the context. We need the system prompt. We most likely always need the system prompt. Do we need to retrieve some documents from our vector stores, from our chunked knowledge base? Do we need some tool results, whether from the current response or from some previous responses? Do we need to attach some documents? And that question has to be answered on every turn. That question needs to be answered on every turn. Like I said, more and more stuff can still go in here. More and more stuff, skills, agents.md, stuff like that. All those stuffs, a lot of them can still go in here. So this is basically what the context part of a harness is all about. Now let's talk about what a good design looks like. What a good design looks like. And first is the fact that you should always have a system prompt. Yeah, you should have a system prompt. You should always have a system prompt. You as the builder of the harness, you must have a system prompt. And what the system prompt does is that it tells the model who it is, or it tells the agent who it is, what tools it has, and what good behavior looks like in the context of its role. It tells it who it is, what tool it has, and what good behavior looks like in the context of its role. Because good behavior when you're a coding agent is different from good behavior when you are a, let's say, travel agent or an healthcare agent. So it defines what good behavior looks like based on its role. This is the control plane of you as the developer, as the agent builder. This is your control plane. This is where you add code your instructions. This is not agents.md. This is not the agents.md, even though agent.md can also go into your context. This is what you define as the builder. Agent.md is defined by the consumer of the agent. You as the builder, you determine the system prompt. The user is the one that writes the agent.md, or let's say soul.md when you talk about things like OpenClaw or Hermes agent. So those ones are defined by the user, and they can also go into the context, but your own hard-coded instructions go into the system prompt. Another thing you need to decide is your history strategy. By the way, I missed out that here, and this is a very quite important part of the context and I missed it out. The conversation history. Yeah, the conversation history. We saw it with the loop, we saw it in the gaps. The conversation history. So the conversation history also has to go with every turn. I think the system prompt and the conversation history, those two, you can't do without them in the context. So yeah, you have to pick what your history strategy would be. How do you pass the conversation history on every turn of calling the model? How do you pass the conversation history? And to a lot of you might just want to say that, yeah, just pass the entire thing. We need to remember everything. Let us pass the entire thing. And yeah, you're right. To an extent. You're right in context. In a context, you're right. Because that is a strategy called full replay. That strategy is called full replay. That's the name of the strategy where you just pass the entire history. But context windows are a limited resource. So you can't always just pass everything. And sometimes too much history is going to confuse the agent. Yeah, the agent is going to be confused because it will be finding it hard to focus on the specific parts of that history that are required for the current operation. So to manage the context window and to also make sure that you're focusing on the main parts that the model requires to respond to its currently given task or the current step it is processing, you then have summarization strategies like compaction. Yeah, these where things like compaction come into play, where you compress all your history into a summary that still makes sure that you are not missing the important parts and the model can still be able to get the required context for the current step it wants to perform. And that's a particular type of strategy. And even from compaction, you can always have pointers that can point to a file in your file system where you actually dumped the entire conversation history. But more on that later. When we get to the chapter on the context layer where we're managing the context and any chapter that has to do with that, we're going to look at these strategies and things like truncation and even how to structure our memory. Whatever strategy you're picking must provide the model enough history that will fit the current task it's about to perform. That is the main thing you have to keep in mind. You have to feed the model what it currently needs to perform the task it needs to perform at that point in time. Another important good practice we're going to be discussing is retrieval. Retrieval. You need to bring in just enough outside knowledge that will be useful for the current task and not bury the model in details. Make sure you're not burying the model in details. Just retrieve what you need. The only thing you need is what should be retrieved. Don't say, yeah, let me just dump this entire book on Python into this model because I just want to write a simple observer pattern. No. Retrieve only what you need because we need to manage the context window. Yeah. The context window is a very limited resource, and every strategy that we're going to be using in performing context engineering is going to be anchored on the fact that we're trying to manage this limited space. Deciding what to include, what to compress, what to leave out, and when. Yeah, that when is also important because it depends on the task that the model is to perform at that point in time. This practice used to be called prompt engineering back then, but prompts are static, and even if you look at all the prompt engineering strategies, they are all static strategies. Context engineering is different because the context is a moving target. The context is a moving target. It's different on every turn. As we have explained, it is different on every turn because the task you're about to perform is going to determine what is going to be loaded into the context. So the design of your context is an ongoing concern and not something you just write one time, like prompt engineering. So, now that we understand what the context is all about, let us do our case study. And this time, we're going to be using Cursor. Enough of Claude Code, let us look at Cursor. Now, Cursor's context engineering is what set it apart from ChatGPT in the early days. I think Cursor was the first time we saw a proper harness in operation. Like, Cursor was just awesome. Everybody was copying and pasting code from ChatGPT. Then Cursor came and like, yeah, you can do it here. You can do it here. And we have the full context. We understand your entire environment. We can create the files for you. We can create the entire project for you. And we are going to always understand what you're doing at every point in time. Yeah, Cursor was the first harness that we actually felt. And honestly, big ups to the guys that created Cursor because they really were ahead of time on a lot of things. So let us look at some of Cursor's context parts. Just some of them, the ones that are very, very obvious. And the first is cursor rules. Yeah. If you are very familiar with cursor, you know what cursor rules are all about. So the first is cursor rules, and this is the system prompt layer. Yeah. This is how cursor does system prompt. Cursor rules. That's the first layer in the context. Every single prompt to the model that cursor is running gets these cursor rules. That's its system prompt layer. Next is cursor's code base indexing. Yeah, how cursor index your entire code base. And this is how cursor does retrieval. This is how it does retrieval. Anytime it is trying to reply you in the chat window, or it's trying to generate code when you are typing, it has your entire code base indexed, and it can retrieve any piece of information it needs from your entire code base in order to be able to know what next to do or how to reply you in the chat window. So cursor's code base indexing, that is where retrieval comes in. The next thing is your currently open file. That's the file you are looking at, the file that you are currently on its tab. The currently open file is your focus. That's where you're currently working. That is what cursor uses as the main point of focus to determine every other thing that is important. That is like its anchor point to really determine what needs to go in the context. So that's the focus. Then you have the file that you have mentioned in your chat window. Yeah, those files that you hit hat and it brought out all the files, and you picked one of them, or you picked like 3 of them. Those mentioned files, those are your attached files. Remember, we have attached documents. Those are your attached files. They are different from the code base indexing where the cursor is doing in the background, and it can always use retrieval to get what is important for the currently open file. But if you explicitly attach any file, it's going to take it as a full attachment. It's going to take it as a full attachment for the current task that you want to perform. And finally, we have the recent edits that you've made. The recent edits that you've made. These represent your history. These edits represent your history. That is the history, what it uses as the main history for what to do next, based on the prompt you are giving it, or based on the code you are trying to write. Every single time that you hit a keystroke, and that keystroke is to trigger a completion, a code completion, every single thing we just described is going to be assembled into the context. Every single thing is going to be assembled into the context to determine what that completion should be. Or if you are chatting, if you are in the chat window, every single thing is going to be assembled to determine what the response is going to be. So like we said, your cursor rules are your system prompt. Your code base indexing is where you have your retrieval. This is where retrieval takes place. Your open file is your current focus, or in the case of code completion, is your current prompt. The files you mentioned with the @ sign, these form your attached files, and your recent edits make up your history. Yeah, they make up your history. So that's basically how cursor works. Cursor is basically just a wrapper, but that is a very, very, very oversimplified way to look at it. Of course, you have the model. They use the same model that we all use every day: GPT-4, GPT-5, Claude this, Opus that. But for cursor, the model sure is the same, but the context is the product. The context that cursor is able to supply it. Cursor being able to engineer the right context to go into every prompt. That is the product. That is the cursor product. And that is why cursor is currently valued at almost $30 billion just for this context. Just because of the brilliance of the engineering around this context. Cursor is basically using an IDE that they forked. Yeah, they are using VS Code. They are using VS Code. The context is the product. The context is the product. And in the chapter dedicated to context, we're going to be looking at how we are going to be composing our context, and even including things like agents.md, so that users of the agent can also add their own explicit rules to the harness. So in this video, we're going to be looking at the fourth harness component, the environment. Yeah, the environment. So you have a couple of tools, but where will these tools operate? Where will they operate? Which runtime will they operate in? Which file system will this read file and write file tool, read and write tool? Which shell will this bash tool execute? Which network will this fetch page reach? Which network will it have access to? Which database resources is this query DB allowed to query? This is what the environment answers, because all these tools are useless without an environment to operate in. Yeah, they're all useless without an environment to operate in. Every tool with side effects needs a target for this side effect. That target is the environment. Every tool has to point somewhere, has to point to something, has to create what it needs to create inside something. And that's basically what the environment is. It's not a big lesson, it's just that simple. The read file and write file tools need a file system. Make.dir also needs a file system. Fetch web page needs a network, and even where to dump its results. QueryDB needs a database to read in, and Bash needs a shell to run in. And the harness is responsible for providing that environment. So what does a good environment looks like? Let's look at what a good design for an environment in the harness looks like. The first design requirement is that it has to be a bounded environment. Yeah, the environment has to be bounded. You can't just allow your tools to run wild in any type of environment they want, or on your entire system. What if they want to RF some very important files from your drive, or even your entire drive? What if a network tool starts to exfiltrate data from your system? It just sends it to some sort of command, what they call that thing, control and command server, and that just consumes all your sensitive information. Or what if you just have this tool that is calling a service and just burning all your cloud credits? That is burning all your cloud credits without any form of threshold, without any form of limitations that have been set, that have been configured. Yeah, you need to define a scope. You need to define a scope for your environment. Your file system needs to have a scope, meaning that you have to restrict it to a particular workspace, and that workspace definitely should not be all of my machine. Your fetch page should actually be restricted to certain websites, certain networks. It shouldn't just be able to go anywhere. You kind of have a white list or a black list at least, so that it doesn't just go to malicious sites and just download malware. Also, you have to point your database to a specific database. Everything has to be bounded. Everything has to be bounded. Even your database tool probably should have the kind of operations it can perform. Probably shouldn't be able to delete data. That should be something you probably should do, because we keep seeing agents deleting data these days. And yeah, if you control that from the prompt angle and you don't have the harness implementing it, then you're going to face some serious problems. Later on, we're going to be seeing something called soft constraints and hard constraints. And soft constraints are basically instructions you gave to your model. Don't do this, don't do that, and all those type of things. Like, oh, don't do this, don't do that. Those are soft constraints. And why they are called soft is that your model can ignore them. Your model can ignore them. Tell your model 1,000 times, don't delete my passwords file in my Linux environment, but your harness is giving it a delete tool that can do anything, that doesn't have a bounded environment. It can ignore that instruction. If it deems it okay, it can just ignore that instruction. So your harness has to be the one enforcing that constraint. And that's where hard constraints come from. Hard constraints are constraints that are enforced by the harness. Soft constraints are basically instructions you're giving to your model, and they can simply ignore it. So that's one thing you first have to realize. By the way, I realized that this is environment. So it's environment. Good. So have a bounded environment. Very, very important. Restrict the scope of where your tools can operate. That target, restrict the scope of the blast radius of your tools. Number 2, your environment should be reproducible. Yeah, you should be able to reproduce your environment. So if you start a session and you want to build, let's say, an hotel management application, we should have a clean new environment. A clean new environment should be created for that. Every task should start from a clean environment. Every task should have its own clean environment created for it. You should not reuse environment across different tasks. You should not reuse it across different tasks. I'm not talking about one task where you're going multiple turns. I'm not talking of one particular session. No, a particular task, like clicking new chat on your chatbot. We all use chatbots, so that's something that you're familiar with. If you click new chat, you should not just dump stuff from the previous chat. No, you should not do that. Later in memory, when we discuss memory, we can see how to pass information between tasks. But when it comes to environment, you create a clean new environment. That's why when you click new task, you just see a blank chat. So that's the mental model you should have for your environment. Whenever you want to start a new task, you should create a new environment. You should not inherit leftover files, mutated databases, or dirty processes from previous tasks. No. Every task should have its own dedicated environment. And this way, when something goes wrong, you can rerun it and see the same failure. And whenever you see that failure, you know that this failure is not from the environment. It's not because I had leftover files in my environment from previous tasks or something bled into my context. No, this is basically coming from the model and the agent itself. Also, your environment should be inspectable. Yeah, we should be able to inspect it. As an engineer, you should be able to see what the agent did to your environment after a run. That is, what files it created, what command it ran, the processes that were spawned and stuff like that. Those things are very, very important, especially when we get to creating our observability framework inside our harness. So your environment has to be inspectable. We should be able to see stuff, see the processes, see the files created, see the folders created. Every side effect to your environment should be visible. Now that we have a good understanding of our environment, let us do our case study. I'm sure you love those. And this time we're going to be looking at Codex. Yeah, we're going to be looking at how Codex manages its environment. Now, one brilliant thing that Codex does is that it runs every task in a sandbox container. It runs every task in a sandbox container. So what it basically does is that it clones your repo and puts it in a sandbox container. Now, inside this container, the agent can read, it can edit, it can run tests, and even execute any arbitrary code without touching your real machine. Everything is done safely inside this sandbox container. And when the task is done, the container will be destroyed. This container will be destroyed, and changes will be sent to your environment as a pull request. Changes will be sent back to your environment as a pull request. So you are only getting what worked. You're not getting all the chaos that happened inside this sandbox container. This is why engineers trust Codex to run any code they didn't write. You can just pull anything, dump it inside Codex, run it. Codex is not going to run it on your actual machine. It's going to create that sandbox, run it inside. You will know whatever is happening with that code inside that sandbox. The sandbox will deal with any type of chaos or any type of malicious intent that might be coming from that type of code. And you don't have to deal with all that. And you can choose to accept it or reject it, keeping your own environment safe. You can even perform experiments inside that sandbox. You can decide to delete some files and see their effect. You can run wild bash commands that you probably didn't write, something you copied from Stack Overflow or even copied from something like ChatGPT. You can also hit the network. You can just browse some very, very strange sites. Everything can be done safely inside that sandbox, because the blast radius of any type of threat has been bounded to a disposable container. Yeah, it has been bounded to this disposable container. Without the sandbox, the same agent doing the same work will be touching your real file system. All your credentials, all your repos, everything. It will be touching them, and I don't need to tell you how dangerous that can be. But with Codex, something that we all fear before and avoid, that's running arbitrary code, it just takes it from a reckless idea and it becomes something that is an engineering practice. Like, oh yeah, let's see how this blows up, and if we see that it blows up, we just destroy this and come back to sanity. So yeah, that's the beauty of Codex. That's the beauty of how Codex handles its environment. In the chapter dedicated to the environment, we're going to also see how we can use Docker as our sandbox, and we can just run stuff inside the Docker container instead of running it on our actual system. How we can use Docker as some sort of sandbox environment. So the next component we're going to be looking at is the memory. The next harness component that we're going to be looking at is the memory. Now, natively, LLMs don't have any concept of memory. Yeah, they don't have any concept of memory. If you send in an input and that input produces an output, that is all for that single model call. This model is not going to remember the input, neither is it going to remember the output it produced. This is all you get. And that's how it is for every single large language model. There's no large language model today that has memory built in. The LLM itself has no single memory. So if you want the LLM to remember its input and its output, you have to build a memory system around it. I know you must have used ChatGPT or Gemini, and you'll be like, yeah, it does remember what I say. We have conversations, we have full conversations. Claude Code remembers my code, it understands my context. All that is powered by wrapping a memory system around your LLM. Every single interaction that you've had with a chatbot, an LLM-powered chatbot, that remembers what you have discussed, what you're discussing, and you can even come back after a couple of days and it still remembers, is as a result of a memory system that has been built around the LLM. And that memory system is not a model responsibility, it's a harness responsibility. It is the harness that is introducing that memory system. And this memory consists of two types. We have two types of this memory, and that's in form of a short-term and a long-term memory. These are the two flavors of memory that are built around LLMs today: short-term memory and long-term memory. You must have heard of different types of memory systems like episodic memory, periodic memory, and the likes. Everything can still be boiled down to these two main memory types: short-term and long-term. Now, what does short-term memory look like? Short-term memory is memory within, let's call it a chat session, if we're going to be going with chatbots. So you open up a tab, a new chat tab in your favorite chatbot, let's say ChatGPT or Gemini. You open up a new tab and you start having conversations with the LLM. Your entire conversation within that particular session, everything it holds in memory so that it can continue to give you coherent answers and follow along with the conversation, is what is termed as short-term memory. Short-term memory within a task. Like if you're going with Cloud Code, you're working in a particular project, you have a particular session, the project, you're not starting a new session. Memory within a specific session is what is called short-term memory. It's what is called short-term memory. These are your conversation history, scratch pads that your model uses to jot somewhere to result when the model calls tools and it returns results, files that you mentioned within the conversation. Everything is within your short-term memory. All that is within your short-term memory. Now let us look at long-term. Long-term memory, on the other end, is memory that can be shared across different sessions. So you start this chat session today, you close it, you have a couple of important items saved to the long-term memory, probably a new user signed up and started a new session. So it saves the information about the new user into the long-term memory. Then when this user comes back tomorrow and starts a new session, it doesn't start to ask the user about their name, their email, and all those profile stuff again. It has saved it. It has recognized from this first conversation when the user signed up that this information is important. So it is saved into the long-term memory store. By the way, this arrow should have been double-edged because we can save stuff and we can retrieve stuff. So it is saved into this long-term memory store. And when this conversation kicks off, let's say the next day or even just an hour after, the LLM can understand, or rather the harness can remember the user by passing the user's information from the long-term memory store into that session. And the same occurs for any other session that is opened after that, as long as that particular information is relevant to that session. So this is where you store things to remember about the user. You can store the user profile, you can store the code base like Cloud Code, you can store information about the code base there. Every single information that needs to persist beyond a single session is stored in the long-term memory store and retrieved as needed. So that's how long-term memory works. Short-term is within a session, long-term is across different sessions. Now let us discuss what a good design of this system looks like. There's still, just like every other part, there's a whole section, chapter dedicated to memory. So we won't be going into serious details here. We're just going to be mentioning a few things so that you can always understand and look forward to them in the section where we focus on this, and in other sections where we reference memory and we use memory. So what does a good design look like? The first thing is that the two flavors of memory have to be designed differently. Yeah, they have to be designed differently. You can't design short-term memory the same way you design a long-term memory. Most of the time, short-term memory is full fidelity, meaning that you keep all the actual messages, you keep all the tool results, you don't leave anything out. Unlike long-term memory, whereby you just look at the entire conversation and you see the useful things that you can extract that are going to be needed for a different session. Long-term is usually compressed. You have things like facts, embeddings, and the budget for long-term memory is quite small. Yeah, the budget is quite small. There's a lot of things filling up the context window. And long-term memory is kind of like, I won't call it low priority, but there isn't so much space reserved for long-term memory because most of the context window is already spoken for. You have the system prompt, you have the active conversation, you have current tool results, and the model within a session will most likely call a bunch of tools. You have also files that have been referenced, RAG stuff that has been pulled from the vector database. So whatever space is left for things to remember from the long-term store is small. It's quite small. So long-term memory is designed around fitting useful information into that small size of the context window. So you have to be saving things that you know are going to be very, very important for another session. For example, like I said, user profiles. User profiles are quite important. Then some preferences, some user preferences, probably they like to be replied in French for some reason. That might be an important preference for the user. Probably they don't like answers beyond 3 paragraphs. They've mentioned it explicitly, so you want to save that and wait for them to correct it before you stop giving them their answers that way. You want to save things like their location if they allow you. You want to save their address, core information. You don't want to be saving any tool result because you feel it's important. You don't want to be saving any type of document that can be retrieved through RAG or can be referenced by the user. You don't want to save all that. You can index the entire code base for something like Cloud Code. You can index the entire code base so that you always have that in memory. You always have pointers to different parts of the code base in memory. But like I said, the budget for long-term memory is quite small, so you want to ensure that you are storing what is necessary and also passing only what is necessary into the context window whenever the task at hand requires it. Remember, these are all singletons according to the LLM. The LLM does not have any concept of memory. So anytime you are filling up that long-term memory part of your context window, make sure that you are passing what is important for the current request. Not for the entire session, what is important for the current request. Another very important design decision is that write triggers are an explicit honest decision. Yeah, you don't want to delegate to your model when to save something in long-term memory. And this is for long-term memory. This is not for short-term memory. This is for long-term memory. Short-term memory is hot. It's full fidelity. You most likely are going to be saving everything. But for long-term memory, you want to be in control of what you're writing into your long-term memory store. For example, you can have trigger points. You can say, okay, at the end of every conversation, you should save anything that is related to this. You can tell it to save a particular information or to save to the long-term memory store when a tool is called or when a specific event happens. The most important thing is that you have to be in control of when you're writing to the store, because if you just leave that to the model, it can just dump in a lot of crap based on what it thinks it is reasonable. So whichever your trigger rule is, whether when an event occurs, when a tool is called, or at the end of every session, this should live in the harness. It should be a clear mechanism that the harness is handling and not the model itself. Now, this is not a rule that is not going to be broken at all. Sometimes we might inform the model on the type of things we want it to store, tell it when to store it and all that, but that we will see cases where we will need to make that decision going forward as we build the harness in this course. But it is important that you control the trigger points and exactly what you want the model to save, exactly what you want to be saved into your long-term memory store. If you leave the model to decide what to remember, get a memory system that saves different things on different runs and is impossible to debug. It's going to be very, very difficult for you to debug what the model's thought process is when it was saving a bunch of stuff that you probably don't need. Like I said, the model should contribute the content while your harness gates the right operations. Also, retrieval from memory is bounded. Retrieval from memory is bounded. Now, what does that mean? It means that we don't dump our entire memory from our long-term memory store into the context. We only pull what is relevant. As you can see, a lot of these things are for, or these 3 items are for long-term memory. So I'm still talking about long-term memory here. So you don't just say, oh yeah, I saved this bunch of stuff. They all seem to be important. Let me dump it into my context window. No, only pull what is relevant. Use retrieval strategies to pull what is relevant from your long-term memory store into your current context window, your current LLM call. Only what is important to the prompt that is currently going into your LLM call. So always keep it bounded. Don't just dump everything from your store into the context window. You're going to end up confusing your model, and that is not going to be seen as a model problem. You can't blame the model for that. Your harness design is the main reason why you are having crappy answers, because you are dumping your entire long-term memory into your context window. So now that we know how memory works in the harness, and we've also looked at what the different flavors are and what a good design looks like, let us look at our harness in the wild, and our case study is going to be Cursor. Cursor also implements short-term and long-term memory. And as you may have guessed, Cursor's short-term memory is simply the chat history within a conversation. The chat history within the conversation that you're having in the chatbot window of your Cursor session. That is where all the short-term memory lives. However, Cursor's long-term memory shows up in things like the add feature and Cursor rules. In your Cursor rules, when you tell Cursor things like, this code base uses snake case, it will remember it across all your sessions. If you tell it that you want to use TypeScript, it will also make sure that it is not using vanilla JavaScript to write your JavaScript code. And you can also use the add feature to reference files within your code base. So you can see that these two systems, also in Cursor, are operating in a different manner. In your chat history, the conversation is live. The old history is being kept full replay to make sure that the model is remembering everything that you're discussing. But then you have things like your Cursor rules that you've defined once, and Cursor understands that these are the important preferences in your project. So it makes sure that it's passing this into every call of the model, passing it into the context window, fitting it into that long-term memory space. And also when you use the add feature to mention any important item within your project, it also bundles that along with that current model call. Two different systems operating differently, even though they are both memory. But like I said, there's a whole section dedicated to memory. So when we get there, we're going to introduce both short-term and long-term memory into our harness build. The next and final component we're going to be looking at is the observability part of the harness. Now, any instrumentation that is built around the harness, built around the model, that is exposing what the model is doing, is the observability layer. Every instrumentation that you construct around the model that exposes the activities of the model is what can be found at the observability layer, or is what is considered to be a component of the observability layer. Now, this includes things like logs of each model call. Every time you call your model, we write logs tracking information about that model call. We also have traces of each tool execution. So whenever the model calls a tool, we want to have a trace of the entire execution stack for that tool call so that we can have that information anytime we need to debug it. We also have latency and token metrics. The time to first token, how long it is taking for us to get our responses from the model, and how much tokens are we consuming in a model call, both input tokens and output tokens, and even get to compute the total tokens for a particular session. So we have this information also that can be gathered for us to have insight into how fast our requests are and how much we're spending on each request. And we also have evals. These help us to score agent behavior. So we pick specific tasks that are critical to the model's operation, we write evals around them, and they score these operations so that we can be able to have accurate information about how well our agent is performing, the quality of responses that we're getting from our model, and how we can always improve our harness to make sure that we continue to get good responses and also improve for better responses. So yeah, these are the types of information that we can gather on the observability layer through the instrumentation around the model, and this is also a very important component of our harness. Now, why do we have to have this in place? Why do we have to have something like this observability layer in place? First is that agents are non-deterministic. Agents can be non-deterministic. They are non-deterministic, they run multiple steps, and they can even run for several minutes or even hours. They can run for hours for long-running tasks. So when something goes wrong, and trust me, something would always go wrong, you need to be able to answer the question, what did the model do, in what order, with what inputs, and also why? Why did the agent perform the action in the first place? What did the model do? In what order did it do it? How did it get to that action? And what took place within executing that action? With what inputs? What went in, and most likely what went out? And why? Why was that step taken? And you can't answer any of these questions without observability instrumentation. You can't. The model itself, if you ask the model directly, it will just give you something like a summary. It can't count its own tokens or measure its own latency and stuff like that. It can't give you that. So you can't get the answers to this without instrumenting an observability layer. And you can't improve the harness if you can't measure whether your changes made things better or worse. We've seen harnesses that got a boost on the harness benchmark, a boost of like 30% increase just by improving the harness. The model was not touched. The model was not touched. The harness was simply improved, and that just shot them up in the benchmark leaderboard. So you want to have an observability layer to help you gather this type of information, to answer this type of questions, so that you can know when your model or your agent is performing optimally, and also areas where you can improve. Now, what does a good design look like? What does a good design look like? The first thing you want to consider when building your observability layer is that every model call must be logged. Yeah, you have to log every single model call, and you have to log it with the full context. You have to log it with the response, the latency, and also the token count. You have to log every single model call. This is your ground truth for anything you want to measure in terms of how well your harness is performing. And as you're logging every model call, also ensure that every tool call is logged. Yeah, tool calls are also first class operations when it comes to an agent execution. So you have to make sure that you're logging every tool call, and you have to be logging it with the arguments, with the results, and also the timing information. How long it took, when it was called, when the execution ended. You have to have all these metrics recorded, because you're going to thank yourself when you need to debug critical issues. In fact, the issues don't even have to be critical. Even simple issues need this information to be properly investigated. Another information that you want to grab is a trace. Now, when you call your LLM, input, output, that's a single call. That's like one unit of execution. Something you will call a span in your telemetry terms. Now, if you have a chat session, within that chat session, you're going to have different back and forth with the AI model. So you send a message, the AI model responds. You send another message, the AI model responds. You send another message, and so on and so forth. Now, every single message you send is a single call to the LLM. You send a message, the LLM responds. That's a single call. So your input, the LLM's output, that's a single LLM call. That's a span. You have another one, and then you have another one. A trace is what is used to group all this together into a single session. This entire conversation is one single trace. For every message that is passed in this session, you have a trace ID that is going to connect all of them together. And what this does is that it helps you to build a session in your observability layer. Because you're just logging model calls, you're logging individual tool calls, a trace is what ties everything together for a single session. And with that, you can replay a single session end to end to see if you can reproduce issues. You can also replay the session end to end when you fix the issue and you want to test if you now have a passing operation. So you also want to make sure that you're saving traces, which are basically identifiers that tie together model calls into a single session, into a single conversation session. So that's also something that we want to have in a proper observability layer design for our harness. And finally, we'll look at evals. Yeah, you should have evals. You see, they're also here. You need to have evals because they are what you use to measure whether your agent is giving you the required results that you want. You design a fixed set of tasks that are going to be your standard for measuring the output. You have outputs that you expect, and then you run your evals and measure the outputs of the agent against your standard outputs, and based on the score you can determine whether your agent is performing well, or you will need to improve your harness, or sometimes improve the amount of information that you're collecting, because you don't want to have false positives. If you don't design your observability layer very, very well, if you're collecting too little information that is not going to be able to pinpoint your exact problem, or you're collecting too much information that you're now getting so much noise, you won't be getting accurate answers. So you need to have clean evals that have been designed to make sure that you're getting proper answers, and then you run tasks against those evals. They are scored against your ground truth, and based on those scores, let's say you have a 0.8, that's like 80%. That looks pretty good. You can always improve that to 0.85 or 0.9. But if you are previously getting 0.8 and you run your evals probably after a model change or you change something in the harness, and you notice that you start getting something like 0.65 or you start getting something like 0.71, then that means your harness has degraded. So evals are what expose this information to you so that you can know when you're doing the right things with your harness design. So one important thing I've learned in systems thinking is that every system is composed of parts, connections, and patterns. Parts, connections, and patterns. If you want to learn a system thoroughly, you need to understand the different parts that make up the system. By the way, let me just move something on the screen so that you know that your screen is not frozen. Yeah, I know that helps a lot of people. Okay, so if you want to learn a system thoroughly, you need to learn its different parts, how they connect, and the different patterns, the different proven patterns of building that system. Or let's say the different proven patterns of composing that system. That's between the parts and the connections. How people have composed that system over the years and the patterns they've discovered to be battle tested. That's one of the best ways to learn a system. So in this video, we're going to be looking at the components we've learned, how they connect, even though we've kind of mentioned it a couple of times. We're going to look at how they connect for canonical harnesses, for standard harnesses. And throughout the course, we're going to be looking at the patterns that have been battle tested for composing these components and their connectors. So in this video, we're going to be looking at the simple standard agent harness architecture in order to understand how the components connect, how they talk to each other. Now, this is our harness. This entire box is our harness. This entire frame is our harness. And the most important thing here is the loop. The most important thing in this harness, the coordinator of this harness, is the loop. Is the loop, as I've discussed in its own introduction video. And what the loop does is it basically orchestrates the activities within your harness. If your harness is going to be single agent or multi-agent, that depends on the loop. If your harness is going to gather the right context, it depends on the loop. If your harness is going to save the right things into memory, it depends on the decisions that the loop is taking. Because an agent is basically a looped call wrapped around an LLM. So the loop is the most important. So when we go into the loop, what happens? We get our prompt fed into the model. Get our prompt fed into the model. This model is going to process our request. Check if we need a tool call or not. Most likely we need a tool call. If we don't need a tool call, we get a response. Yeah. But most likely we're going to need a tool call. So a tool is called, let's say web search, file search, whatever it is. The tool is dispatched by the loop. The tool then produces results. And this tool execution and the result is produced happen in the environment. The tool executed in the environment, the results are in the environment. So we observe these results. Have we gotten to the final answer? Most likely no, because the task we want to perform will definitely take several steps. So these several steps are going to be running in this loop. So we check in this environment for our result. We observe our result. Then from our result, we'll determine what we want to save into memory. What do we want to save into memory? Of course, we want to update the conversation history. That is very, very important. So we want to save that into the short-term memory. We also want to save tool call results and some other stuff that is important to the second cycle or to the subsequent cycles of this loop. So we save that into short-term memory. Then for long-term memory, we extract important information from what just happened, if any. So this is not a compulsory step. But if you discover any important thing, you extract it. And this might not even be the trigger point for your long-term memory. It might be when a tool is called or when an event happens anywhere within this loop. Anyway, for memory, we have short-term being updated at every turn and long-term being updated by your triggers whenever necessary. Once we make sure that memory is adequately updated, then we need to fire the next turn. We need to fire the next request to our model. And this is where context engineering takes place. Because we now need to arrange the context. We need to arrange the next context that will be fed into the model. Our conversation history, tool calls that are relevant to this next turn, RAG retrieve documents based on what this next turn requires, static data, context rules, so many things, system instructions. We assemble everything for the next turn and we fire our next call. And we keep doing this over and over and over and over for every single turn, for every step in the task, until the task is complete. Yeah, until the task is complete. And when we resume this loop, we have our long-term memory to feed stuff into our context to help us remember what we're working on. And we continue to run this, continue to run this, continue to run this until we finish the current session that we are. So this loop continues to run as long as you're interacting with your harness. Everything your harness is doing, whether you are the one interacting with it, whether it's the harness recalling itself, whether you are in a Ralph loop or whatever, this whole process runs over and over and over until an exit condition is met. And outside that, you have all the observability instrumentation that is collecting information from this entire process. Just mining information from this entire process and saving it into a dashboard, probably using something like Langsmith or Langfuse. Those dashboards are very, very detailed when it comes to all these model operations. They're going to show you what the RAG operations are. They're going to show you the full context that your model is being called with, every single tool call, drill down the tool calls so that you can pinpoint the input, the output, the execution time, and everything. Show you how much tokens you're consuming for your model. Even show you thinking tokens, the amount of thinking tokens that you are consuming. So yeah, this is the simplified agent or harness architecture. This is your simplified harness architecture. And as we go further in this course, building out our harness, you'll be seeing a lot of decisions that we'll get to make to build what I'll call the harness of our dreams. And even in production harnesses, you still encounter a lot of intricate decisions. A lot of engineering decisions go into composing all these parts and even some other sub parts, orchestrating this loop to ensure that the harness or the agent is in the exact shape that we want it. So throughout previous lessons, we've been looking at a real harness like Cloud Code, a real harness out there in the real world, and comparing, or rather looking at how our components exist in these harnesses. We looked at Cloud Code, we looked at Cursor, we looked at Codex too. We also looked at Codex. But now this video is for you to see everything all at once within a single popular harness. And I've chosen Cloud Code because it's the most popular. Cloud Code, Cursor, I don't know which, I don't have the numbers, but I believe currently Cloud Code is more popular than Cursor. So we're going with Cloud Code. So we're going to be looking at each of the components that we've looked at and how Cloud Code implements these components. Just to kind of decompose a real world agent into the components that we just discussed. So first is the loop. By the way, if you like this diagram, yeah, I do too. Gemini did this. This was from Nano Banana. I was trying to draw out this, then I just remember that Nano Banana is quite good at creating diagrams like this. So I just basically took my notes and dumped it into Nano Banana, and Nano Banana took my notes and gave me this diagram. I had to do a little bit of tweaks, but yeah, I still got something good, and that's why you see this AI symbol here. Anyway, yeah, just giving you a background just in case you want to create this type of diagrams. So first we have the loop. And like we know, the loop is the agent's outer orchestrator, is the agent's main orchestrator. Mostly uses the React pattern. That's the most popular pattern. That's also the pattern we're going to start with in this harness build, in this course, and we'll continue to improve on it. And what this does is that it keeps calling the model. It keeps calling the model until the task is done, until there is there's always a condition. There's always a condition that needs to be met. So we have to check. So you say it keeps calling until the task is done. So there has to be a criteria, a completion criteria that will continue to check after every turn. If it is met, the result is going to be returned. If it has not been met, then we keep calling this React thought, action, and observation process. So that's what the loop does. It calls the model, decides action, execute tools, and inspects the tool, checks whether the result is gotten or a step budget has been hit, because that's one thing that you also want to make sure that you have a step budget. You don't want this loop to continue forever. So for every task, you want to give it a step budget like 15 or 20 or whatever you feel is reasonable for the subtasks to be completed and for you to get something reasonable. And if it doesn't complete it in those number of turns, it will just package what it has and return it as the result, so that can be passed to the next execution, which is fine. That one will just take off from where the previous one stopped. So that's the loop. Next, we have tools. Claude Code has simple tools. That is very simple tool surface, as we've discussed. Tools like read, bash, glob, grep, a simple task management tool for writing out your plans when you give it a task. It also has an MCP connector, and Claude's main ideology is to have simple tools that are composable, so that you can get so many customizable tasks done using simple tools. It's easy to compose simple tools than to have all these bespoke tools, and you have to keep creating a bespoke tool for every single task that you want to perform. So these are Claude's basic tools, and it also adds more of these base tools that are easy to compose. That is basically how Claude operates. And you can always add your own skills. More on that later. So these tools are basically sharpened for specific tasks, and like I said, easy to compose. Then we have the context. And Claude implements this with different strategies. There's the system prompts that we are familiar with. We also have the conversation history. We have the tool results, which are important. Then we have this thing called agents.md, which is one of the simplest ways that harnesses implement long-term memory. Is basically a file, so it's not like you have like a vector store and RAG processes and all that. No, it's just a simple file where instructions for the task is going to be defined, and also this file gets updated with new information that needs to be persisted as the task runs. Now, Claude on its own actually implements this as Claude.md. That is the agents.md version that Claude uses, but you can still use agents.md in Claude. You can then use your Claude.md to refer to agents.md, because agents.md is actually the main standard, and we're going to be building out a system for that in our harness too. Agents.md is the main standard used by OpenCode, used by Codex and different other harnesses out there. But Claude has to be stubborn, so they went with Claude.md. But you can always refer to agents.md within your Claude.md, so that you can continue to use agents.md, which is the standard. Then you also have art files. You can also pull files in with your art references. And yeah, this is how context is assembled in Claude Code. Then we have our environment. Yeah, the Claude Code environment, which is basically your local machine. Your file system. Claude has all the tools for reading and writing to your file system. It can also run shell. You can also run in your shell. That's a bash tool to run in your shell. We've talked about the MCP connector, which also comes from tools. As we have looked at earlier, the environment is just a playground for tools. Yeah, environment is basically just a playground for tools, and you can make that environment remote. You can make it scoped, and you can also make it your entire system, which is not advisable, but sometimes you just gotta do what you gotta do. You also make sure that you are getting destructive operations, which is something that Claude also does, to make sure that your actual system is protected from any kind of shenanigans that your model might decide to do. Then we have memory. Short term and long term. Like I said, agents.md is one of the clean ways to implement simple long-term memory. Put your instructions, instructions that need to persist, context about the project you're working on, and stuff like that. You put that in your .claude directory. The .claude directory in Claude, where you can dump information like that. And you can have different layers of agents.md. We're going to be looking at that later. You can have different layers of agents.md. You can scope them to your repo, or you can have them at user level. You can even have them like at a system location on your system, so that every single project that you're running can actually inherit from those instructions. I think I saw that with OpenCode. But we're looking at Claude Code here. So, I believe it does something similar. You can have like system-wide instructions for every Claude Code instance that you spin up. Then we have the observability and log system. Claude Code will show you every tool call in the UI, so that you can know what is going on. It also tries to collect its own information, because it needs to debug when you ask it why something failed. But basically, the one you see in the UI is basically the tool calls that it is making. Every read operation, every edit operation, every bash operation is shown to you as it happens. So basically, this is Claude Code, and this is how it implements every single component that we've looked at. And I want to believe at this point you're getting kind of theory fatigued. So in the next section, we're going to start building out our harness.